programming quite, interestingly. In case of a traditional programming, you have a computer, you provide it with some data, which may be, for example, some unsorted lists of integers. And you also provide it with a program, which is a sequential set of instructions carrying out which you could actually synthesize some predefined output from the data, like sorting the lists of integers. Okay, that program is already provided to the computer by some smart human being. And then the computer just clerically executes those instructions. On the other hand, in machine learning, we provide the computer with some data, and we also provide the computer with some example output, what we want out of that data. So we can provide it with the unsorted lists of integers and the corresponding sorted lists, and we expect the computer to learn how to sort the lists of integers. We expect the computer to write down the program for itself. That's the dream goal of machine learning. Okay. So if we look into a specific realm of machine learning that is called supervised learning, it is most simply expressed in this mathematical form y equal to f of x. X is a vector or a matrix comprising of certain numbers which sitting together specify a piece of data. So if you ask me what is data, anything around us which could be abstractly represented to a computer in terms of bits and bytes qualify as a data. Even when I go to a bank and apply for a bank loan, I become a piece of data, and I become specified in terms of my CIBIL score, my credit rating, my fixed deposit amount, and so on. So X is that abstract representation of a piece of data. F of X, it's like a factory in which X enters like a raw material. So this f of x, this function is the machine learning system, and y is the outcome from the system, which is a pre-specified category in which x should belong. So in order to create this machine learning system, you must provide a training set of labeled examples. So some part of the data must be labeled by some expert. Like you hire a doctor, and the doctor is looking at, his time is very costly. So the doctor is looking at maybe 200 chest X-ray images of randomly sampled patients and visually classifying them into normal bacterial pneumonia, COVID-19 induced pneumonia, and benign, okay, by looking at the white patches of fibrosis inside the lung X-ray images. Once the doctor puts these images into these three pre-specified categories, now we can use these labeled images to create this sort of a machine learning system, which when a new chest X-ray image comes, which is unseen for the machine learning system, this system should be able to predict its correct category. It's much like this. So the features of the image goes into the machine learning system, which is denoted as f of x, and it should return what is there inside the image, what is the category inside the image. It should take a decision about the pre-specified category inside the image. If we confine ourselves to computer vision related tasks, this is not really very easy for a computer to classify images into different categories. When we look at a motorcycle image like this, we immediately capture its wheels, its handle-like shape, engine pipes, and so on, and we immediately call it a motorcycle. But what the computer records or what the camera records is huge pile of numbers like this. Even if you take a small portion of the image, it is described in terms of these numbers which actually quantize the brightness of different points. Okay, these are the grayscale intensities. Okay, and from such piles of numbers, it is never easy to conceptualize what the object is, how it looks like. For example, if I suppose just pick up 2 pixels from 2 random locations like this, and we represent this image in terms of these 2 pixels only. I suppose mount a camera on the doorway of my garage, and I would like to distinguish between cars versus non-cars. I don't want a cow or an elephant to walk into my garage, right? So if I represent each image in terms of these 2 pixels only, since they are randomly sampled, they can come from any location, completely statistically decorrelated. What will happen? The cars and non-cars will get into a complete mix-up in this 2-dimensional feature space. All these points represent one of such entities. plus for cars, minus for non-cars. They will become a khichuri. We cannot distinguish between them. But on the other hand, if we use two small submatrices, 3 cross 3 or 5 cross 5 matrices, which when dragged over the image horizontally, scanning the image, one such small window, as soon as it detects a handle-like shape, it gets us a very high number as output, okay, through spatial convolution. And other window, as soon as it gets a wheel-like shape, it gets us a very high output response near 10. So suppose if it doesn't get a wheel or handle-like shape, it will give us a response near 0. Now, if I plot the responses of these two feature detectors, one is the wheel detector and the other one is the handle detector along the x and y axis respectively, the non-cars will accumulate far away from the origin, because for these points, both the detectors will give us a very high response. On the other hand, the cars will accumulate very close to the origin, and it will be very easy to demarcate between them even by a linear classifier, even by drawing a straight linear boundary between the two classes, okay? So a lot of it depends on feature representation, how we are going to specify our data items to the computer. And human beings, you know, they are visually very good feature extractors and as well as the classifiers. Okay, if you look at these 16 images, 8 from each class, sheepdog or mop, you can immediately know what is what, which one is a mop and which one is a sheepdog. Puppy or bagel, similarly, if you look at these images, okay, maybe you take 15 seconds or so and then you realize which one are dog puppies, curling, and which one are bagels, okay. Barn owl or apple, not only you tell me what is what, but you can also tell me what are the abstract and higher level features, higher than the pixel level measured ones. We are not talking about pixels. Human mind doesn't recognize image in terms of pixels, okay? We immediately capture the abstract and high level features, and you can tell me, okay, for the owl, the distance between the two eyes are much greater than that between the seeds of the apple. There is a ridge-like structure indicating the nose of the owl. There is no such structure just below this, these two seeds. Okay. This is the most dangerous data set. So you see, we have Chihuahua and Muffin. So you can tell me that, okay, for the Chihuahua, the dog puppy, the eyes and nose, these dots are arranged on the vertices of a regular triangle. However, the cherries on the cake are very haphazardly arranged in most of them, and there may be more than 3, okay? So, but these data sets qualify as very hard ones, even for the latest deep neural learning systems. So we are habituated to see science fiction movies, and we may be tempted to argue that the machine learning these days have become almost like a silver bullet. It can be used anywhere, it can solve any problem like that. But this is only myth. Machine learning should be seen as an assistive technology these days, especially deep learning, which works like this straw that this modern pro uses to suck up the water instead of putting pebbles after pebbles inside the jar and waiting for a long time until the water comes to the mouth. So, with this background, what does deep learning offers to us? This is the traditional machine learning circle. In fact, if you look back at the last 40 years history of natural language processing, text mining, computer vision, video analytics, the major problem was how to represent an image or a video or a text document or a speech signal in terms of the most suitable context-aware, abstract, and high-level features. Different human feature extraction algorithms, handcrafted feature extraction techniques were developed. For example, in computer vision, we had the SIFT, scale invariant feature transform. We had wavelet features, Gabor filter coefficients, many such textrons. However, those techniques were not uniformly good over all possible types of images. So the traditional machine learning technique employs the human feature extractor who will extract the context-aware high-level features, and then the data represented in terms of those extracted features will be presented to a classification system, which will decide to which pre-specified category we should put this object. On the other hand, in deep learning, we have a layer-wise connected huge network of simple mathematically processing nodes in each layer. This network actually gets us rid of this handcrafted feature extraction. It can, in an automated manner, extract the most important abstract and high-level features, and then it can do the classification. Context aware. So that means, you see, different features may become more important in different classification contexts. When we are talking about classifying between birds versus non-birds, okay, presence of feathers, presence of a long beak, a tail, these features become very important. On the other hand, if we try to classify between cars versus non-cars, then whether the central object has some wheels, has an engine pipe, has a steering, these things become very important. So it varies. And the deep learning systems can extract such high-level features in a context-aware way by minimizing the same final cost function through a mechanism that is popularly called backpropagation. Now, coming to deep learning, there are two deep inference models, deep prediction models these days. One is the traditional discriminative or predictive deep learning model, which is very happy to learn a right decision boundary between the two classes, as you can see here. So left side of this line, it is the blue class, right side of this line, it is the red class. That is the classification rule that which is discovered by the discriminative or predictive model. On the other hand, generative deep models are quite new, and this is where we are going to concentrate for the rest of the time. The generative models, classification is secondary for them. They try to estimate the underlying spatial probability distribution of the points or samples or representative data points from the different classes. They try to estimate this spatial distribution of points from the different classes. And it's a very old problem in statistics in very low scale. For example, many of you may know, if you are working in machine learning or statistics for some years, you know, if I give you 10 random numbers, just scalar numbers, 2.6, 3.8, minus 5.7, etc., and I ask you, return me the Gaussian distribution, tell me the mu and sigma, the mean and standard deviation of the Gaussian distribution from which these 10 numbers are most likely to have been sampled. So, you know, there are very good algorithms like maximum likelihood estimate or maximum a posteriori estimate, Bayesian estimation for doing that. But instead of 10 scalar numbers, if I now give you 500 images, each image is 100 pixel by 100 pixel. So there are 10,000 pixel level features specifying each image. If I give you this sort of high dimensional objects and ask you, now you return me the multivariate underlying probability distribution from which these images might have been generated, then usually there is no guaranteed statistical methods to solve this problem. So since 2014, a machine learning research group started using neural networks for such high dimensional estimation of the underlying distribution. Thereby came GAN. And before that, there was in 2013, there came the variational autoencoders or VAs. They try to estimate this underlying distribution. And once they are able to do that, they can sample from that distribution. What does that mean? That means they can create very photorealistic, but completely artificial or synthetic objects. They will create the camera clipped face of a human being. I will show you such results. You can see the gray hairs, you can see the wrinkles on the face, but that person never exists on Earth. Completely artificial. Synthesis is possible for nowadays, of course, not only for images, but for text documents, for voice signals, for speeches, everywhere. That is where the generative models lead us. Okay. So deep neural networks, once again, till 2010, we were very happy with these small squeezed neural networks with only one or two hidden layers. After 2012, after the publication of the famous ImageNet classification paper, everyone started to add as many hidden layers as possible in their neural networks, because from the lowest level, pixel level features, combination of these features into abstract and higher level features like ages, then face parts, then face prototypes, all these flow happens through the hidden layers. Okay, so as many hidden layers, the expressibility of the neural network increases. But there is a point of caution. If you make your network deeper and deeper, the number of trainable parameters also increases, and the network becomes more hungry for training data, and the risk of overfitting also increases. We will touch upon them. So this was the 2012 breakthrough in predictive learning. It has, I think this is quite older number. It has 60,000 plus citations by now. So this paper was published in the Advances in Neural Information Processing Systems, or NIPS. Now it's called NeurIPS conference, and it reduced the error rate on ImageNet classification. ImageNet had 1.5 million images from various internet sources distributed over 1,000 plus classes. So this paper, after the publication of this paper, in fact, the company started, investing huge amount of money, especially Google, Adobe, Samsung, Facebook, all these big giants started to invest huge amount of money behind deep learning research. Google came up with DeepMind and other similar concerns, and the networks became more and more complicated. Okay, nowadays 150 layers in a deep network is not of a big deal. So inside a convolutional neural network, which is one of the de facto standards until now for image classification, what happens is, if you give an image as input through two operations called convolution followed by max pooling mainly, and with a suitable activation function like the rectified linear unit or ReLU, the most abstract and higher level features are extracted. What is meant by, I am repeatedly saying abstract and higher level. This means, see, pixels are like, they're very close to the machine, the pixel values. They're like a executable code, which is written in machine language. Human beings are not able to interpret it. On the other hand, so when you look at the face of your friend from a Facebook group photo, you do not look into the face like, okay, the top left corner pixel is 162, beside that 187. No, you immediately capture some very interesting and higher level feature close to human beings, like there is a cut mark on the chin, nice beard, nice mustache, etc. So through convolution and max pooling, such higher level abstract features are extracted and packed. We call it flattening. Through flattening, they are packed as a vector like this. This vector is provided to a fully connected neural network near the final layers of the convolutional network. And this short fully connected network, which is actually shallow, this short fully connected network actually provides us a classification. Just hold on for 1 second, please. Sorry for the interruption. So now you see, so this abstract and higher level vector is provided to the fully connected layers, and which makes this sort of classifications. So this is convolutional net in feed forward way. We give an image, from the image is summarized in terms of the most abstract and higher level features which are packed, which is much small dimensional. If the image is 100 cross 100, that means there are 10,000 pixels in the image. This vector is only how much? I mean, this may be simply 500 into 1. So it's a 500 or 200 dimensions maybe, which are extracted from this image. So all the components of the vector indicate presence of some abstract and high level features inside the image. Okay. If we if we reverse the flow of the CNN, we have this. Then what happens? So if you see this structure, before the fully connected layer, we provide an image. The image is summarized in terms, the abstract and higher level features are extracted through these layers, and the final output is a vector comprising such higher level features. if we reverse the flow, we can give a vector as an input to the image, to this reverse network, and it can create an image like this. Finally, this is called deconvolutional flow or deconvolutional network. Now, coming to generative adversarial network, it was a 2014 breakthrough by people from University of Toronto, Canada, and the Mila Research Group. Mostly Ian Goodfellow, he was at that time a PhD candidate. This was his PhD work. And GANs, as I said, GANs are most effective in synthesizing fake or artificial images, text documents, translating the style of one image into another, and many such things it can do. So when GAN was trained with portrait images from medieval period artists all over Europe, so GAN created this in 2018, GAN created this its own medieval period charcoal portrait painting called Edmond de Bellamy, which was auctioned for US dollar 432,500 in USA. And you can see in place of the signature of the artist here, the paintings are signed by the artists. So here you can see this is basically the objective function of GAN, which is written here. So let's have a look towards this particular and fascinating neural architecture, and then we will see what it could do. So any probabilistic modeling relies on two concepts. One is there will be many samples or observations coming from the real world, and there will be synthetic observations coming from a model. Model means a machine learning system, a neural network, or combination of such neural networks. So from that model, synthetic observations will be generated. Observation, this is a very favorite term for the statisticians because they imagine all the data objects like an image or a text document. These are observation of some underlying stochastic process which is governed by some probability distribution. That is why they often use the term observation. Here, observation, you put it simply as to mean some images. Okay, so from real world, we will have images which are examples, and the model will create synthetic images which are similar in spirit but not carbon copy of those real world images. So the category of these two images must match. Sorry. So like all numerical methods, what GAN probabilistically performs is something like this. It starts with a very easy probability distribution like a uniform distribution, and then it transforms iteratively this distribution into a more convoluted multimodal distribution, which should mimic the probability distribution of the images under our disposal. So now we directly go into the internal structure of a GAN. GAN uses two neural networks. One is called a generator and the other one is called a discriminator. So the generator takes input from the random noise vectors. These vectors may be generated randomly from a uniform distribution. Every component could be either +1, or every component could occupy any two values with 50% chance, or these vectors can come from a multivariate random Gaussian also. Output of the generator network is basically an image. So the input is a small dimensional vector, which initially comes from random distribution, and the output is an image. So you see, the generator could be built by using a deconvolutional neural network that I was just talking a few moments back. So, and the other neural network is called discriminator. The input of the discriminator is an image, and the output of the discriminator is a score between 0 and 1. It's a real number between 0 and 1. If the input image is good, if the discriminator feels that the input image is good and realistic, it will give it a score very close to 1. Otherwise, it will give it a score very close to 0. So the generator and the discriminator has access to the external example images, like images of various Hollywood celebrity faces. GAN should be trained with images of different categories or kinds. So, for example, the training set could comprise of such celebrity faces. The discriminator has access to them. So the discriminator can compare the images generated by the generator against the images coming from the real world, and it can give scores accordingly. And these two neural networks actually involve into a competitive learning scenario. They compete with each other. Generator is like the student who is trying to generate very good images, imitating or following, not directly imitating, but following the guideline from the discriminator. And the discriminator compares the images generated by the generator against the best images coming from the real world training set. And then it provides a feedback in the form of that scoring function. Okay, that scoring function. So the discriminator guides the generator to do even better and better and better, so that it can extract almost score of nearly 1 from the discriminator. So we say these two neural networks play a two-player zero-sum game with each other. It's like tug of war. If in a zero-sum game, this is a game theoretic terminology. In a zero-sum game, if one party wins by ₹5, the other party will lose by ₹5. So the total profit is always 0. Now let's see it in somewhat greater details. So the generator, the neural network generator, takes up such code vectors and converts them into image. Initially, these images will be ghostly images without any pattern. Why so? Because it's much like the generator neural network weights and biases are not trained. Okay, they are just random. They start with some random values. And therefore, they will not be able to generate any meaningful image. It's like you give a 3/4 years old young kid a pen and a paper, and she just draws some random patterns on those papers because she's not trained into painting. Am I clear? So every generated image will be, associated with a code vector like this, which comes at the input of the generator. So the generator neural network generates an image, and ideally that image should be very close to some meaningful realistic image. If I train GAN with the handwritten digits type of images, then the generator image should be close to one of the handwritten digits in Roman numerals in English digit system from 0 to 9. On the other hand, if we employ a neural network classifier, when we provide an image into the neural network classifier, it gives us an output vector like this. And this output should be close to this sort of a one-hot encoding. So if this is the difference between neural network generator and neural network classifier. On the other hand, the discriminator is another neural network which is more like a two-class classifier. Its input is an image called X, let's denote it by X, and output is a real value R. This real value R is lying between 0 and 1 usually. If the input image is very good, realistic in nature, then the output score will be very close to 1. If the input image is very bad, as you can see here, the output will be very close to 0.1. That's the job of the discriminator. It is also called the evaluation function, potential function, etc. Now, can we use the discriminator feedback to generate objects? The answer is yes. So the general algorithm for training the discriminator goes like this. Given a set of positive examples, these are the real world training images coming from outside, from the user. You must provide GAN a lot of example images. Only then GAN can generate new images of the similar category. That's the deal. So given such a set of positive examples, we will use the generator, which is initially untrained, to generate the negative examples, the poor images like this. And in each iteration, the discriminator learns basically a two-class classification to discriminate between the positive versus the negative examples. Where from the negative examples come? We employ the generator. The generator generates 10, 20, 30 images in batch. Out of that, those images for which the discriminator at current situation provides maximum score, D of X, we take those images for the training of the discriminator in the next phase. So put it simply, the discriminator is like a two-class classifier. It has access to the external training set from which it randomly samples a batch of positive examples or good images. The generator is used to generate a batch of negative examples or poor images. Then the discriminator is trained and the output the output of the discriminator is in such a manner that it generates a continuous floating point number between 0 and 1. So the generator is used to generate the negative examples from the discriminator. So generating the negative examples once again, we provide the codes to the neural network generator. It generates an image. That image goes to the discriminator. The discriminator gives it a score. Usually, this image is this in-between image is not displayed to the user. It's like a hidden layer. And then the discriminator score is updated until the generator is able to get somewhat a good score. So the generator is updated, keeping the discriminator fixed, till the generated images can secure good score from the discriminator. This process is done via gradient ascent. We will see how. So during this process, the discriminator is fixed. Now the updated generator is used to further improve the discriminator. And during that process, the generator is kept fixed. The generator weights are not altered. Okay. So there are two neural networks. Their training goes in an interleaved fashion. Their training goes hand in hand. And one is trained while the other one is kept fixed to its current configuration. Let's look at it. So we initialize the generator and the discriminator with random weights and biases. Let's call these parameter sets as G and D. In each training iteration, we sample some real objects from the training set. We generate some fake objects from the generator like this. You see, initially these objects will be just ghost-like. The discriminator is trained with this training set. The discriminator weights are updated by labeling these training sets as positive and negative examples, 1 versus 0. Once the discriminator is updated, it is kept fixed. The discriminator weights are kept fixed. Now this fixed discriminator is used to criticize the generator. The generator now generates images of various kinds from random codes. The discriminator is providing each of these images some scoring function, some score. Based on the score, the generator is updated such that it can extract maximum score from the discriminator. Once it reaches that maximum level of score, now the generator is fixed. This improved generator is now employed to further update the discriminator. The improved generator generates improved set of images, and that helps the discriminator to understand the finer categories, finer levels of distinction between these generated images and the real images. It's like there is a school, there is a very strict teacher who wants the school students to secure very good marks in the final. So the students are writing some model answers for their questions and submitting to the teacher. The teacher is not happy, cutting those answers, they're giving small marks, little marks for the answers. So the students strive a lot to write in a more better way to represent their answers in very good manner until the teacher is very satisfied. Now the teacher gives 9 out of 10 or 9.5 out of 10. Now the teacher attends a teacher training camp where the teacher is being aware of the first boys and first girls from other surrounding schools. So the teacher becomes aware, okay, these boys and girls have so high standard, so I must make my school student standard even better. So when the teacher returns from the training camp, the teacher again starts giving poor marks for those improved students. So earlier when the teacher was giving them 9.5, now the teacher will give them, say, let's say 7.5. So the students start again improving their writing standard, and this goes on. So here also you see, initially the discriminator is updated, keeping the generator very poor. Then the updated discriminator's feedback or criticism is used to improve the generator. Once the generator is improved, that updated generator is used to further modify the weights and biases inside the discriminator, and this goes on until they reach a situation where none of these two networks could be further updated without deteriorating the other one. This is ideally where they should reach, and we then say it has reached the state of Nash equilibrium, okay, after the famous game theorist and economist Professor John Nash. So this is the learning cycle of the discriminator, and this is the learning cycle of the generator, and they go hand in hand. So if we look into the objective function of GAN, actually both the neural networks obey the back propagation type algorithm. They go on updating their weights and biases based on the gradients of a single objective function, which also is called the minimax gain value function from the game theoretic perspective. The design of GAN involves game theory. Okay, so the minimax objective function looks like this. I hope this little bit of mathematics should not make you very frightened. So you see there are two E symbols. This E stands for expectation, which is proxied by the average. Capital D of X is basically the score given to an image X, which is X tilt P data, means this image is sampled from the real training data set. The underlying distribution of the training data set is denoted as P data. So capital D of X is the score given to the discriminator to the real image. Log of that has been taken and averaged over the batch of images. On the other hand, Z tilt PZ means this Z is a noise vector or codebook vector coming from an underlying noise distribution. This noise vector goes into the generator. G of Z is the image created out of the noise vector by the generator. That image is presented before, I said discriminator is like a teacher. So that image is presented before the discriminator. The discriminator assigns a score to it. That score is D of G of Z. So inverse of that score is 1 minus D of G of Z. We take the log and then we average it out over the batches of images. That is, this average is actually represented here by expectation. Expectation in such real situations when we do not know the underlying distribution could always be approximated by the average. So this is the discriminator output for real data X, discriminator output for the generated fake data GZ, as I said. Now, from the perspective of the discriminator, it wants to maximize the objective functions because it wants to push up this D of X towards 1. For real data, it wants to give very high marks. And for fake data, GZ, it wants D of GZ to be as low as possible. That's thereby pushing up or increasing the second term. So from the discriminator's point of view, both the terms must be maximized. And it's a maximization problem from the discriminator point of view. Initially, we must, train the discriminator. That is why we must maximize. That is why this maximization step comes in the inner loop. On the other hand, with respect to the generator has nothing to do with the first term because generator do not have access to the real world training images. The generator tries to minimize, the generator tries to minimize the second term only. Why so? Because the generator tries to generate so beautiful images. The GZ should be such that D of GZ should be close to 1. Therefore, 1 minus D of GZ should be very small, close to 0. Log of that, log is a monotonic function, so that should also be very small. So from the generator perspective, it tries to minimize this overall objective. So the training of these two neural network alternates between gradient ascent on the discriminator. Gradient ascent is just the reverse of gradient descent. Instead of following the negative gradient direction, we will follow the uphill, the positive gradient direction. So the gradient ascent on discriminator, because it's a maximization, and then once the discriminator is trained, it will be fixed. And then we will have gradient descent on the generator, and we can use this second term only. But still there is a problem. If we use this term log of 1 minus D of G of Z, if you plot it here, log of 1 minus D of G of Z versus D of G of Z, you will see a flat, long portion of the function. This is how log 1 minus X versus X looks like. So this flat portion, which is very small, that means in this range, your generator is not doing good. Log of 1 minus D of G of Z is, so if you look at this portion, D of G of Z is small, 0.2, 0.3, etc. That means your generator requires further improvement, but this portion is flat. So if you try to draw tangents at different points of this portion, they will be having very small slopes, which means the gradient is of very low magnitude. That is why if you try to incorporate a deep neural network, it will suffer from the vanishing gradient problem. In order to alleviate this problem, Goodfellow in his original paper, they proposed that instead of minimizing log of 1 minus d of g of z, it's same as maximizing log of d of g of z. So if you see the function log x versus x, or log of d of g of z versus d of g of z, you see this function has a nicely changing slope of the tangent over a big portion of it. So the gradient value is not that small. This is called a high gradient signal, this green one. So that's why in the current implementations of GAN, instead of gradient ascent on generator, we use instead of gradient descent on this earlier function, we use gradient ascent, and we maximize this objective function because it has a high gradient signal over the regions where the generator performs poorly. That means where we really require more changes in the weights of the generator. That is how the GAN training goes on. So this is the overall algorithm. We update the discriminator by ascending its stochastic gradient. Now you see we are replacing the E notation. Here this E notation may bother some of you. So we just proxy this expectation operator with the averaging operator over M samples from the real world and M samples generated by the generator. So this is the step where we use the discriminator update based on the gradient over this objective function, and here we update the generator by using the gradient over this log of d of g of z portion. So in fact, three situations can come up. One is during the GAN training. One is the discriminator is calling a real image fake by assigning it very low score. This is the false negative scenario. In that case, the discriminator weights must be updated. On the other hand, true negative scenario where the generator generates a fake image and the discriminator gives it a very low score. So who is doing bad? The generator. Who requires punishment? The generator. That's why the generator weights must be updated. On the other hand, false positive, the generator generates fake images and the discriminator says it's real. The discriminator is very happy. So now who requires further updating? The discriminator. So these three situations proceed hand in hand during the training of GAN. I have already, okay. So this is a visual representation of the convergence of GAN. You see the real data is distributed on this blue circle and the generated data are the orange dots, which initially start from a random distribution and gradually converge to this blue circle. We are comparing GANs versus variational autoencoders. Variational autoencoders are also sometimes very useful as a generative model, but their convergence usually takes much more time, as you can see, for certain distributions. However, GANs are not meant for such easy distributions of points. GANs are meant for something a lot more. So when GANs were trained with pictures of horses, sofa sets, churches, cycles, etc., GAN generated its own horse pictures, bus pictures, church pictures, etc., none of which exist on Earth. So this is how the GAN images evolved with time. These are taken from this progressive GAN paper. So you see, in 2014, we did not have the luxury of using GPU or tensor processing unit, TPU, like parallel computing architecture. So at that time, the GAN generated images were like this. But now the GAN generated images have become photorealistic and up to a very high resolution. So you see this lady, you can see her finer details on her face, and it's like a camera clicked image, but this lady does not exist. It's a ghost image. None of such human being does exist. Similarly, this person, etc. Not only faces, the recent Big GAN project from Google DeepMind, it can generate very meticulous, realistic images from different classes of the ImageNet dataset. So this pasta, this fountain, this coffee cup, all these pictures, they're all fake. They were never really photographed on Earth. Okay, that is what you could do with the help of GAN. And nowadays, not only images, but text documents, voice, speech signal files, everything could be manufactured by using different types of GAN architecture. The GAN research is at its boom. A new GAN is coming almost every week. You can see this GitHub repository called GAN Zoo, and you can see how the cumulative number of papers on different GAN architectures just mounted over years very recently. Now, I don't have enough time. I will conclude in next 5 minutes or so. But before that, let me tell you one of our work. The gentleman data is basically the machine learning. Success of machine learning systems depends on how well behaved your data is. So when we employ any classical deep or shallow system, like starting from k nearest neighbor to residual nets, we assume that all the classes are equally represented in the training set. All classes have good number of example samples inside the training set. If there are internal variations within a class, the sub-concepts within the given class, they are also equally represented. Like if I want to make my machine, my neural network, distinguish between apples versus oranges, within the apple class, there are green apple, reddish yellow apple, yellowish red apple. So all these sub-concepts, sub-types within the class must be properly covered in my training set. Similarly, all the classes should have similar class conditional distributions. All the feature values must be defined. All the feature values must exist, must be recorded for all members of the training set. If any of these 5 assumptions are failing, not obeyed, then we have data irregularity. Life is hardly so easy. So we are plagued with data irregularity, a big taxonomy and review of which could be found in this paper. And when such data irregularities come, especially class imbalance, which means the number of points in the training set from one class is hugely outnumbered by points from the other class. This very often happens in multiple practical scenarios. And when such data irregularities gather inside your data set, your classifiers look like this. They become completely confused and give us very abrupt and bad results. Okay? Class imbalance is a scenario where data from one class has very few samples compared to the data from the other class. This very often comes in case of, let's say, for example, credit card fraud detection. Number of fraudulent transactions could be of the order of some thousands compared to number of genuine transactions recorded over a week, which could mount up to some crores. Okay. Similarly, we could have identifying a rare disease from medical images, like cancer, malignant tumor identification, or something like that. So this is basically fraud detection, identification of malignant tumor, anomaly detection, natural disaster identification or prediction, like cyclone. Bad events will be much lower than good. Thank to God. Usually bad events are still much lower. Therefore, they create the minority class. This class where we have very few samples, this is called the minority class. So there are many things said about it. So this is the scenario in class imbalance in deep learning era. Deep learning classifiers are highly affected by such imbalance. Wang et al. In NIPS 2017 came up with the SUM397 dataset, which has 397 classes. And the classes appear along this long-tailed distribution. Some classes appear very few times, like the public library images. Those images, 10, 12 such images compared to several thousand images of drawing room. Okay, so SUM397 is the example, classic example of a multi-class imbalance data set having 397 classes with a long-tailed distribution. Now, in the deep learning era, people also call it long-tail classification problem. Long-tail because many classes near the tail area of this distribution have rare presence. Okay, so I will not, I don't have time to speak about all these things. Let me just churn out the basic idea of GAMO. So GAMO is one of our works which uses for image classification with severe imbalance. GAMO uses an oversampling technique, which is called generative adversarial minority oversampling. That's a short form of GAMO, and it appeared in the ICCV 2019 conference. ICCV is one of the top most conferences in computer vision. All the codes and other details could be retrieved from this arXiv link. We have GitHub links inside the paper also. So let me just tell you what it does and then conclude. GAMO oversampling means the minority class has very few points or very few data items. The classifier becomes biased towards the majority class. You see, if you have only 3 from one class and 97 from the other class in your data set, training data, and if your classifier misclassifies all the 3 examples from the minority class, which could be cancerous, okay, those people must be warned right now. But your classifier says, okay, all are good, benign. So your prediction accuracy will be how much? 97%. So you will see, oh, it's a very good classifier, 97% accuracy. But what is its use? Negative, 0. Negative, in fact, harmful, because it misses completely the minority class. So one way to get rid of this situation is that let us create more synthetic samples in the minority class so that the population or size, the size of the minority class is also nearly 100 and the majority class is already 97. So now the 2 classes are almost of equal size. The classifier will not get biased towards the minority class. In case of image classification, GAMO uses a 3 neural network GAN architecture. We call it a 3-player GAN architecture, which can very effectively create artificial images in the minority class to balance the sizes of the 2 classes. And let me just get rid of all these mathematical things and let me just tell you how it functions through pictures. So these are the 2 classes. One is highly populated and dense, the blue class. The other one is sparse and with the red points, which are just few of them are there. So this is the minority class. Unaided classifier means if you apply a classifier which simply has nothing more to do, no auxiliary mechanism, it creates a decision boundary like this one between the blue and this yellowish region. Many red points are in the blue region, which is for this deep blue class. So these red points are misclassified. The classifier says these points to be in the majority class. It's like people coming for the diagnosis of some disease that even if they show the signs of lung cancer or breast cancer, your machine learning based system says you are normal, go home, you can take rest, etc. That could be really dangerous. On the other hand, if we use a convex generator and a classifier instead of a discriminator, we can use a classifier to criticize the points created by the generator. Are they in the overlapping region of the 2 classes? Are they good enough? Are they hard enough for the classifier? That feedback is provided by the classifier. This is also a GAN-like architecture. Convex generator restricts the new points inside the convex hull of this minority class. If I do that, then fine. All the red points are now rightly classified, but multiple blue points are misclassified. So there is a huge set of false positive, which could be very dangerous. People don't have cancer, the system says you have cancer. That could be equally dangerous. GAMO creates this sort of a distribution of the points and equally populates the 2 classes by using a convex generator, a classifier, and a discriminator. The discriminator provides an additional feedback to properly place these green plus signs, which are the artificial points, to cover this minority class area. That's what it does. Actually, there are a lot of other details which I cannot elaborate here because of the lack of time. These are some comparative study results and so on. And let me go towards the conclusion. Okay. So the future is, of course, deep neuroevolution is one of the very interesting facets coming in future. All the deep neural networks have multiple hyperparameters. Hyperparameters are the structural parameters of the network. That means when you design a deep neural network, how many hidden layers are sufficient for a particular data set? How many neurons should be kept in hidden layer? What type of activation function may be used? All these are hyperparameters which are usually fixed based on trial and error mechanisms. So neuroevolution tries to evolve the structure of such a deep neural network, including GANs, by using the principles of Darwinian evolution and natural genetics. And Uber AI recently is investing a lot of money behind this. It's a scalable alternative for the search of the rightmost structure of the neural network. This recent paper in IEEE Transactions on Evolutionary Computation uses such an evolutionary mechanism to evolve the generator part of the GAN, keeping the discriminator same. Cycle GAN, style transfer, is nowadays one of the hot topics where cycle GAN, this paper also was published in ICCB 2017, and it is one of the benchmarks in this area. What this system does is, if you click a photograph of a region by your camera and provide it to the cycle GAN, it can tell you how that photo looks if it would have been drawn by famous artists like Monet or Van Gogh or Cézanne. So it transferred the style of an image into another while preserving the content. Now, in 2021, we are working with cross-domain transfer. So you write a line of text, it can generate the image matching that description. It can convert the vocal style of one person into another person's vocal style. So such that, I mean, this deep learning lecture is delivered by some famous film star. The voice quality is coming from the film star, but the content is mine. That sort of vocal engineering is now possible nowadays. Neural photo editor, for example, is a behavioral photo editor. You keep the cursor anywhere and it will adapt this hairstyle according to your image. Pix2Pix is another image-to-image translation system where it can convert these inputs into output, sketches into original photos, black and white to color, input labels into this output original structure of a house. All these are possible with back-end GAN tools and bringing older photos to life. This is a very interesting example. You give some input expression, it can superpose that expression on archival quality painting like Mona Lisa. And it will show you how Mona Lisa looked like if she imitates your expressions. So with all this backpropagation and other methods, are we really any closer to how the human brain functions? Geoffrey Everest Hinton, who is also the pioneer of, who is not only the pioneer of the deep learning field, but who also devised the backpropagation algorithm with his co-authors long back in 1986, the famous Nature paper. That paper's title had the word representation learning. So after so much developments in machine learning, so much craze around it, Geoffrey Hinton believes we are light years away from actually understanding how human brain really believes. But we are making baby steps towards it, as science always does. So he said, the future depends on some graduate student who is deeply suspicious of everything I have said. Maybe some completely new mathematical models emerge in future, which will change our conception about these learning technologies to a great extent. That's why keep on doubting, have the courage to ask questions on all established theories. These are some resources I would like to acknowledge before I close, especially in machine learning. All such materials are available free of cost because thanks to the open access movement by the machine learning pioneers. So with this, I would like to close, and if you have any quick question, we can answer these things. Thank you very much for your kind patience. Let me welcome some questions from your side.
Thank you so much for the wonderful presentation, Professor Das. And here we have some questions already.
Okay, in the chat box. Okay,
yes, in the chat box.
Okay, so let me read it. To achieve better ghost images, do we need more real-world images? Yes, this is a very interesting question. Thank you, Mustafizur. Actually, yes, in case of GAN, initially the images that are coming from the generator, they are of very low quality, mostly ghost images. But as discriminator is provided with more and more real images from the real world, the quality of the generated images also improve. But you are right, GAN is very much hungry for training data. Okay, usually the rule of thumb is if your neural network has X number of trainable parameters, weights and biases, number of training images should also be of the order of X, maybe 1.2X or 0.9X. So if your neural network has 1000 trainable parameters, number of training images should be 900 or 1100 is good. But if you have 200 training images, your neural network won't train easily. It will suffer from what we call an overfitting error. Same thing happens to GAN also. Usually, if you employ convolutional neural networks as the components of the GAN, which are very heavy networks, which could have almost 1 million parameters, so at least number of training images should be of the order of 1 lakh or so. Okay. Otherwise, they are going to suffer from overfitting error. This is a very important point of concern. That's why people nowadays are mostly into few shot generative learning. Few shot means very limited number of training images they try to employ. And that's natural for human being. If I want to make my daughter understand what is a giraffe, I can show her only one picture of giraffe. She can go to a zoo and identify a giraffe very easily. But for a neural network, you need to show it 500, 600 giraffe images. So few shot learning tries to get rid of that. Okay. And then there is another question from Mohammad Rakibul. Okay, thank you very much, Rakibul. I have a question. Is normal computing power is okay to try GAN architecture? See, normal compute, it depends. It's a very good question. It depends on how big training set you are going to handle. GAN can work with small neural networks with very few trainable parameters if you are trying to generate very easy patterns like MNIST images. Okay, MNIST, you know, the handwritten digits. But if you are trying to generate high resolution, complicated image, which may have now pixels of the order of megapixels. Okay, 1 megapixel image. 1 megapixel is nowadays nothing. All of us carry 20 megapixel plus mobile phones. So 1 megapixel means 1000 pixels by 1000 pixels. Okay, 10 power 6 pixels. So if you want to generate such high level images, you have to rely on GPUs and high level architectures. Low level normal computing power, you can also train GAN with that, but your generation will be of, in case of MNIST, like very simple handwritten images or characters, you can generate nice quality images, but not high resolution photorealistic image of human faces or other things. That's why you should rely on Google Colab, and you can use the Colab very nicely provides you with this high level GPU, Google GPU powers, at least for a fixed amount of time. So you can try your hands over there. Thank you.
All right, so if there is no other question from our audience, then we'd like to thank everyone. Thank you so much, Professor Das, for your time.
Thank you very much.
And for the beautiful presentation. And thanks to the participants for joining. So I hope you all have a very good day. So we'd like to conclude our session here. Thank you very much. Have a very good day. Bye, everyone.
Bye-bye.